All right, welcome back. This week we're finally starting to transition to that middle third of the semester. The plan was to do that on Friday, but it was a good use of our time. We reviewed the exam instead, and we're going to start by talking more about CPU performance. And one thing you'll find is that this material in the textbook is pretty early in the book. It's in that chapter one of the textbook, and we waited a little bit later in the semester to cover it. I think it's a little bit too not necessarily abstract when it's covered first, but maybe it's a bit too trivial when it's covered first. It talks about performance in this sort of idealized vacuum, but now that we understand a little bit more about computer architecture, now that we understand MIPS and MIPS assembly, at least at some level of detail, I think we'll have a better appreciation for what's happening from the performance equation side of things, and it'll allow us to reason a bit more fluently about what's happening for the various design decisions that we're potentially making in our own implementation. Um, so this is our lecture number 5 material here, and it is covering that early part of chapter 1. Um, there's a homework 5, which is kind of a bridge homework assignment. This week's quiz is also kind of a quiz that's sort of a bridge as well. But we are really finishing up MIPS assembly at this point. We're done covering new aspects of it. My assumption going forward is you know it all. You're fluent in it now. But we'll still keep learning as need be. Instead of writing programs, we'll be trying to understand the performance of programs and trying to understand how these programs execute on our processors. And that'll be our next big topic after this week will be so-called single cycle processor. We're also going to likely find that a lot of that topic is actually review. We've been covering it in bits and spurts as we've gone, as we've tried to understand different aspects of the ISA implications on microarchitecture. We've been doing that within this framework of a single cycle implementation. So while the textbook has a whole half a chapter talking about the implementation, and it could be a useful reference as you're building your own version in the labs. In class, we've covered a lot of that already, so a lot of that will really be review for us. So when we talk about performance, where it gets tricky, and to the extent that it ever gets tricky, is really in two aspects. And the first aspect is primarily, what does it mean to have a certain level of performance? What is the metric that is most relevant for us? And this is the textbook example given. Well, if we weren't talking about computers at all and we were talking about airplanes, well, what would it mean to say that of these 4 airplanes, that one has the best performance? And it's a bit of a contrived example, but the idea here applies equally to computing as well. What is quote unquote best is really dependent on what it is you're actually interested in measuring. And likewise, when designing, what your goal should be really depends on what your optimization targets are as well. You can build a very large airplane or a very small airplane, a fast airplane or one that has longer uh, carrying capacity. Um, and then there's all sorts of potential hybrid metrics as well that are potentially of relevance for both the airplane example as well as for our computing example. So in the very first week of the semester, we talked about latency versus throughput as a way of comparing things. Even that isn't really so straightforward. We have to be very precise when we talk about computing performance if we want to say such design is better than some other design. And we usually can't say such thing with a blanket statement. It has to be within certain caveats we give with regards to what we are in fact measuring. So that's the first, not gotcha, but first thing we have to keep in mind when discussing this topic. And the second consideration we definitely have to keep in mind when discussing this topic is recognizing that it's kind of similar to what we potentially do with our physics type questions as we do reasoning about physics problems. I think it's easier than the equivalent physics problems, but we have to really keep track of what units we're using as well. So firstly, we have to be very aware of what metrics, what are we actually measuring, what's relevant to us to measure. And secondly, as we're doing that analysis and doing that measurement, are the units that result, are they reasonable, and are they correct for our purposes? Um, so physics maybe brings up some bad memories for some people. I'm talking physics 1 stuff, not even physics 2 stuff, and most of you took it at Iowa Western anyway. Um, but the kind of physics I'm talking about, okay, so since that brings up bad memories, right? Then the nice thing about this class is our math really never gets any harder than say 4th grade math in this in this class, and that will remain the same for this topic as well. If we weren't measuring computing performance, and let's say we were measuring a physics one concept like um, running speed. So let's imagine a physics one question where you have a runner. Here, I'll draw a runner. There's a runner. In fact, specifically, there's your faithful professor who you may not realize is an avid runner. And the question says this your instructor is going to run for 1 hour, and he's going to run at his typical pace of 10 meters per second. And so, physics one question, or maybe even like a high school physics question, is well, if that was the scenario of running for 1 hour at 10 meters per second pace, how far? And I'm trying to just explain here in this very simplified example what does it mean to really reason about your units to make sure that you're measuring what you think you're measuring and the result makes logical sense. So the first thing that I would want you to do if working on this physics problem, and the analogy does hold for our computing performance problem, trust me on this, bear with me for about a minute here, that if I were to ask you how far did the runner go, did I go, you would want to make sure your answer, or at least you would have some more confidence in the correctness of your answer if you know that your result was some function of distance or some metric that measured distance. And in this case, likely, we'd want to make sure that we were measuring if we have our speed in meters per second, we'd probably want to make sure that our actual result uh, was measured in meters at the end of the day, right? And what I say the physics one approach to answering these kind of questions is keeping track of those units as you do it. And if you do keep track of those units and you make sure the units make sense in the end, it's not a guarantee that your answer you've come up with is correct, but at least it's some sort of logical answer that you've come up with. In this case, we can just do the unit conversion, which is all this problem really requires, right? The distance that would be traveled would be a function of running for one, but not just one, running for 1 hour, right? And I'm deliberately keeping very clear track of the units that we're using. And we would want to convert that to maybe seconds so we can use our meters per second. So we know in an hour there's 60 minutes per hour, right? That is a metric, or that is a unit we can use here. 60 minutes per hour. And we know that in each minute there's 60 seconds. And then finally, me, the runner, running for 10 meters every second. And we know that this kind of works out because we can sort of cancel out the units. Just like we multiply the numbers out, we can also sort of multiply the units by each other, sort of cancel out the intermediate value. So we know that we have hours, which can cancel out with hours, minutes cancels out with minutes, and seconds cancels out with seconds. So we wind up with the result of, for that hour, I ran for 36,000 meters, which seems about right for me. The issue here isn't the question itself and getting this really great result of running efficiency. It's if we had done this math and if we couldn't remember, well, do I need to multiply that by 60 or is it divide by 60? If you wind up with a result that instead, and this would be an example of an incorrect result, if we wind up with a result that looks like something like 1/60th hours squared per meter or something, that would be a pretty good hint that what we've done was incorrect, right? That in keeping track of the units, if the end result is something nonsensical in terms of those units, I mean, what does it mean to be something in terms of hours squared per meter? It's a sign we did something wrong, right? It's a sign that we did the conversion incorrectly. We divided when we should have multiplied, or vice versa. And the same analysis we would do to our computing systems in terms of the units is actually exactly the same um, for our computing systems as it is for this physics one sort of running example here. Um, Instead of worrying about meters per second, we have a verbiage in computing that relates the clock frequency of our circuit to the amount of instructions we have to run for a certain program, and we have to keep track of those and have a result that makes sense at the end of the day. That's my takeaway here. Not my blazing fast speed, which is a secondary takeaway, but but the point of keeping track of units. It's it's arguably a little bit tougher. There's probably more variables in play for measuring computing system. That comes up in a class like a computer architecture class in the context that we have an understanding of what's happening at the microarchitectural level, and we can make some assumptions about what is happening at the levels below it. So we could say our target is 3.4 gigahertz for this clock frequency of this processor, but we are really measuring at that level and below. And we have little knowledge, or we can only measure, we can't really optimize for what's happening at the layers above us. So the overheads associated with our operating system, with our system libraries, with how we're doing a certain type of multi-threading, and how different workloads are playing along nicely or not nicely with each other, that becomes a very difficult thing to measure. So oftentimes, when measuring computer architecture performance, for measuring the stuff we do in this class, we really take kind of a clean room approach to it. And that's a little synthetic, perhaps at the end of the day. It's if we're analyzing this design in a clean room, in isolation from the rest of the world, from the rest of either the software running on top of the current software we're running, or any other workloads that may also be trying to run in parallel, what kind of performance do we have of the resulting architecture? And even within that, there's a couple different metrics. We had already talked about this a little bit earlier in the semester that we may be interested in potentially latency, which is a performance metric that would be measured in time, right? How long does it take for my job to run? For a single application, what is my stopwatch time associated with it? That can be phrased in different ways, but generally, when we're measuring performance with regards to the latency of an application running, our final metric is going to be in terms of time. Our units for our final metric is going to be in terms of time. And that's a very common thing to measure for a computing system. Lots of different ways we would describe the problem at hand. The end result is under this set of assumptions, how long does it take to do something? Whereas our running example is we would want it distance in terms of meters. Um, for our computing example, for performance for latency, our answer would be in terms of seconds generally, or some unit of seconds, right? How long does it take to do something? That is one common performance metric. Another one is throughput, and they can be opposed to each other, but they can be related to each other as well. Throughput is more of a measurement of how much things can happen over a period of time. That is, if it's a database system, how many queries can you process per minute? Or if it's just a multi-threaded system, how many jobs, how many applications can the machine run at one given time? That tends to be a measurement of stuff per second, where stuff isn't well defined for us yet, but that's what we would measure when we're measuring throughput. How much tasks can I get done per unit time? It's a little bit closer to our speed metric for running, but it's not quite that either, right? The closest analogy to our meters per second would be our clock frequency, which is how quick is our time step for our computing system. Our throughput isn't measuring that; it's measuring how many things can I generally get done over an average period of time. And from within that, the question of whether a given architectural change improves latency or throughput isn't always necessarily that clear. It depends on what specifically you're measuring. So the two somewhat rhetorical questions at the bottom here are, if we upgrade a machine with a new processor, what is actually getting increased? It's not really that clear. Presumably, one machine with a new processor, we're going to certainly improve our latency. But depending on the new processor, we may also improve our throughput. Whereas if we add a new machine to the lab and we're running jobs across all the machines inside that lab, we're likely only improving our throughput of how many total jobs per day can get executed by all of those machines in the lab. But we do, and maybe you're already seeing the point here, we do have to be pretty precise with what we're actually asking about computing performance. And so when I say that these are physics 1 problems, that's to help you out. It's not to try to make things more complicated than they have to be. It's let's keep track of the units, and let's make sure that if the question is asking about distance, let's make sure our result is in meters. And if our result is in hours squared per meter, we probably did something wrong. Let's go back and take a look at it again. Likewise, if our question is about performance And if it's asking about, latency of some operation, our answers in computing performance is likely going to be in terms of time, in terms of seconds. And if we get a result of instructions squared per cycle cubed, we did something wrong there as well, right? And that's okay. Let's just go back and make sure that we did the multiplications where we were supposed to, we did the divisions when we were supposed to, and so forth. So in terms of our performance and our latency, even that question of how long it takes to do a single task isn't actually all that well defined for us, or at least we have to be a bit more precise with what we're saying. In a computer architecture class, where we're focusing primarily on the processor's performance and not the rest of the entire system's performance, we tend to want to care about this final metric listed here, which is user CPU time. That is literally the amount of seconds spent in your processor executing the assembly instructions corresponding to your program. But that is actually different than CPU time as a whole. The CPU is in any multi-threaded system, in any system with an operating system on top of your user software, underneath your user software. Um, the CPU will potentially be doing other things as well. That gets hard to measure. Now you're benchmarking not just your architectural changes, you're also benchmarking how those architectural changes interface with your operating system and potentially other jobs that are happening on the system as well. And then on top of that, you have the rest of the components of your system that also impact that what's called wall clock performance, the actual stopwatch performance, and that's your elapsed time. That is, I hit start on my application, I start a timer, some system timer, I measure the time elapsed from which I hit start to when it's finally returns a value and is actually done. That is the elapsed time. And I'm not suggesting that one of these metrics is better than the other. They're all very useful. If I truly want to know what is the real world performance of this application, elapsed time is your best judgment. If I want to also then determine, how much of that performance is due to the CPU that I'm working on and its interaction with the system as a whole, then that CPU time is also very important. If I'm just looking at measuring the kind of things we're optimizing in this class, which is microarchitectural changes, maybe some compiler optimizations as well, and how that impacts the number of cycles and the corresponding amount of time it takes for your code to execute, it's that third one that's most relevant to us, that user CPU time. The truth is, though, certainly when you're looking to purchase your next laptop, um, elapsed time is what's relevant to you. Who cares if your CPU is super extra efficient if your overall system performance is bottlenecked by something else, right? And if it's spending all its time accessing your hard drive, and so consequently it's slower than this other laptop you could have purchased. The CPU is just one part of the whole. So ultimately, in terms of a real world benchmarking, we do care literally how long does it take to run your code. That does matter. When we're looking at these micro architectural design decisions, we need to look at a little bit of a lower level and sort of isolate what's happening on a cycle by cycle basis in your processor. That's what the user CPU time is going to help us, and that's what we're going to primarily focus on. So instead of reporting our execution time in seconds, we're often going to use just the clock cycles instead, because we know that we can do a direct conversion between our execution time in seconds and a number of clock cycles. It's not one versus the other. It's just a question of which one is easier to reason with. Um, I would say the equivalent to our super fast running professor. Um, and that's enough making fun of me in the chat. Thank you. I invite you all to come down to Des Moines on a typical Saturday with Dr. Jones and I in our running. Um, that's fine. That's fine. But okay, the equivalent of our professor running at a certain rate would be our processor executing at a certain rate. And I think we've covered this before, but if we're thinking instead of our somewhat shabbily bearded professor, and instead it's our processor. And our Intel processors used to have this great sort of Intel Inside kind of branding, but now instead this is a MIPS class. This is our MIPS Inside processor, and it has some sort of equivalent speed metric associated with it. We have fabricated the processor, and in the end result, after we've done that fabrication, or we have a target goal for it, at the end result of all that fabrication, we have a certain clock frequency associated with it. And maybe this point is obvious. I just want to make sure we're all on the same page here. This processor will get some speed rating associated with its clock of something like, for example, 1 gigahertz. Hertz, right? It's something per second, some repetition per second. In the context of computing systems, a 1 gigahertz processor, and giga would be 10 to the ninth here, or billion, would correspond to a processor that ticks 1 billion times with 1 billion cycles per second. Let's make sure I get that right. And I could use it in the units or just say 1 billion cycles for every second. And that's one of our fundamental assumptions as we're measuring our computing performance, right? We have a clock frequency associated with our processor, and that's although there's reasons it can change dynamically over time, but we assume that our circuitry at least is operating under a fixed clock frequency, and that would be that 1 gigahertz. So when I say my processor is running at 1 gigahertz, giga is 10 to the ninth, so 10 to the ninth cycles per second, and that's the equivalent of saying that we have a clock cycle time or a clock period, and we would just take the inverse of that, would be just 1 nanosecond. That'd be a measurement of seconds per cycle. So if we think of the speed of our runner, not in terms of meters per second, but maybe another way to draw the analogy would be, how frequently is your foot hitting the ground? I guess you can't hear that. How frequently is your foot hitting the ground as you're running, which is maybe a secondary running characteristic one could measure, your cadence, right? Um, that is the equivalent of what our processor is doing. If it's the analogy is it's running, this is the speed at which work is getting done in that processor. 1 billion cycles every given second. Or conversely, it's the same metric here. If that's 10 to the 9, you invert that 10 to the negative 9 is 1 nanosecond of time elapses for every cycle that is being executed here, right? And we go back to our fundamental issue of designing any synchronous circuit, of which our processor is included in that, where we can always visualize any synchronous circuit we design as being logic that is traversing two flip-flops or two registers, if we think of it that way, and an somewhat arbitrary amount of combinational logic between it. We've drawn this picture before, but now we can reason about it in terms of our performance equation. So it's good to bring it back up. So we have our sea of combinational logic. There's our gates and wires, not just gates. And if you think to your lab for processors that I saw a lot of people making great progress on this weekend, and I know you'll all get finished up this week, it could be visualized as that. Absolutely, right? We are reading from our register file, reading register 1 and register 2. We're doing a lot of stuff with that register file. Maybe we're reading from memory, maybe we're just computing a result in our ALU, and at the end of the instruction, we're storing the result back into our register file. So in that case, both this flip-flop and this flip-flop are the same physical flip-flop, but in terms of what's happening, we're reading on one side, we're writing on the other. That's our sea of combinational logic. And certainly our model sim tools that we're spending all of our time on are primarily just focused on the correctness of what's happening inside all that logic. Does it give us the result that we are interested in? And starting on this Friday's Fun Day, as well as working into next week's lab and beyond, we'll start to worry more about this. But from a performance analysis perspective, it's important to remember that the timing of this circuit is limited by how far those wires have to travel and what they have to travel through. That if this is our timestamp where we're doing the register read here, and our goal is to have the instruction done in that single cycle, we effectively have that one single clock period to do so. In this case, if we say it's a 1 gigahertz processor, all of the work that needs to get done in any clock cycle has to fit within that 1 nanosecond period of time. That is a definitional thing here. That is the path that it takes to execute this logic between that flip flop being read, the register being read, and the register then being written to update it through that cloud of combinational logic here has to have all paths be shorter than that 1 nanosecond. And there's many such paths, right? It's going to keep growing very quickly, right? Even just think about your register file and the muxes and all the different logic that that register file is doing. And again, that's just right now um, in model sim behavioral simulation, where it's just kind of trying to tell you functionally what are all those paths supposed to be doing. Once we finally synthesize the tools, it'll force us to lay that out onto a chip of some sort and tell us exactly the length of those paths ultimately, both through the delay, through the actual logic, through the gates we require, as well as how long the wires wind up being. The wires physically have to be placed somewhere. Some are going to wind up having to be stretched out a little bit to be able to place things where they need to go. Of all those paths, one of which, and we've covered this before, so if this sounds really familiar, that's fine. One of these paths, this is definitely one of the big picture concepts of this entire course. One of those paths is going to be longer than the rest. It can be a tie, it doesn't matter, but conceptually, one of those paths is going to be longer than the rest. That is our critical path. That's just the term of art that a synthesis or other tool would use to tell you as we're figuring out the timing for this circuit and the circuit for our processor. There's a millions, billions of paths inside that design, one of which is longer than the rest. That critical path is going to be a description of logic, and the synthesis tools will give you some pretty opaque description of it, but it'll literally tell you from this bit through this logic and through this sea of logic, we got to this bit, and here was the length of the path. And that length of path is going to be measured in time. It could be physically measured as well, but and some function of the speed of light and electrons, like getting excited and all that. But generally, it tends to be abstracted away and measured in terms of time. There's a critical path, and it's a physical path on your chip that's being designed, and it's measured in terms of time. And that critical path is what sets the resulting limit, the upper limit on the clock frequency of your circuit. So this isn't arbitrary, I guess, is part of the point I'm trying to make. Likewise, my critical path of running is cardiovascular fitness, pain threshold, whether Dr. Jones decides to really pick up the pace this week or if he's slacking like normal. There's an upper limit there as well. This limit is something we can measure. We don't have to kind of guess at it. Oftentimes for the problems you'll be working on, it'll just be told, assume a 1 gigahertz clock and solve the problems accordingly. But we can measure it. And for the designs that we're doing this semester, we will measure it, and we will be told for your processor, for your single cycle processor you are implementing to start the semester out, here's the hundreds of thousands or maybe millions of paths. Here's one that just happens to be the longest one. And here's the length of that path, generally measured in time, measured in nanoseconds in this case. And if we want our MIPS processor to execute at 1 gigahertz, we have to design it such that the critical path is no more than 1 nanosecond. Okay. Um, and we'll get back to the performance equation in just a second here. In terms of our single cycle processor, in terms of uh, yes, it's the longest path. In terms of our lab design to date, we actually can start to reason about what our critical path is going to be. Now, we don't have the design completely finished yet, but we know the logical steps that are required, right? In terms of our register that's being read to start our instruction as it's executing in our design, it's actually not one of our register file registers, right? What is the register that we read to start the execution of our instructions? It's got a special name. Don't all jump out at once. What is that register for our actual implementation? I was mentioning lab 4 is register file to register file, and that's fine for lab 4. As we're implementing the entirety of the processor, what's actually the first register we have to read to execute our instruction? Definitely a register. I can start drawing it. Got that little symbol that indicates there's some storage and it's relative to the clock. Close enough. The program counter, right? Uh, Instruction address pointer. It's got other names for it, but for us, for our implementation, we have that first stage of the execution of any instruction, and that for Lab 4, we don't have instructions yet. We're just inputting the control signals manually. But as we started to design this, we recognized that um, we need to know which instruction we're executing, right? So there's that first stage of execution, which we've generally called instruction fetch. And I'm just going to label it as IF right now. Take the program counter, determine what address should be our next instruction, fetch the instruction from memory. So there's a physical instruction memory happening there. Next, and I'll just walk us through the stages and for one final time for the purposes of this point. That's our instruction register, that's our register read for the purposes of our critical path analysis here. We then have to fetch the instruction. Well, we've fetched the instruction, we've had a 32-bit value. We next have to decode the instruction. Convert the 32 bits of that instruction to the control signals that we know feed the rest of the processor. Right now for lab number 4, and this is really the last time this semester, you are still manually generating the control signals, but we've talked about how there's sort of a spreadsheet approach we can take. From opcode and maybe function code, generate all the control signals you need for a given set of instructions. And we've mentioned in the past that that can also be when we actually do our register fetch. So that's a second register read, but we have our initial register read happening here. We then have to actually execute the instruction, right? We take those register values that we've read, as well as the other control signals, and we've done our actual math that we may need to do. Our add, our shifts, our other stuff. And for some instructions, we're done at that point, right? For some instructions, we've fetched, we've decoded, we've executed, and we just need to write that result back into the register file. But we know now that there's a certain class of instructions for which we've actually done, and this is our Lab 4 class of instructions, we've actually done the execution in our ALU, we've done an add operation, but we've really only just generated an address in that add operation. And so there's a separate stage where that data address now has to be used. This could have been called DM or something. It can be referred to that, or just memory stage. If it's a store word instruction, now we're done, right? Store word does the pointer math, takes the base register as the immediate offset, calculates an address, takes a separate value from the register file, and writes that value to memory. It's done at that point finally. Whereas our load word instructions do all of those same things, except it's reading from memory. It's not writing to memory, and it's writing back into the register file. That's oftentimes referred to as a write back stage. I'll put /register file again here because it is using the register file at that stage to write a result back into our register file if the instruction requires it. So the question is, all of this, and I'm adding a tone to the question that you didn't add when you typed it up. All of this is happening within a single cycle? Well, it can be, right? That's the design decision we get to make, right? That is the definition of our critical path is just this. Through any set of flip-flops in our design, there's one path that's going to dictate the clock frequency, the longest path that's going to dictate the clock frequency of what our circuit can operate at. One such design decision for our implementation, and if you've been following, and you have been, if you've been following the labs to date, maybe you can recognize that our design decisions have been following that, in that we've been getting all of this done. Yes, so far we haven't done it all yet. We've done a lot of it though. You're a lot further along than you may think with regards to this. We haven't done instruction fetch and we haven't done decode yet. We've done the rest basically. Project Part A is really fleshing out this unit, and then Project Part B is just kind of connecting it all together. And you have 4 weeks to get that done. That's so simple. You're just gonna have so much free time the rest of the semester. You're not gonna know what to do with yourself. But yes, that is our implementation strategy, and that's how we can start to reason about the performance of our MIPS implementation. And I would add that, we talk so much about MIPS and what's unique about MIPS because that's just the assembly that we learn the best. That's what the textbook covers. But this set of operations of fetching instructions, then decoding, then executing, then potentially accessing memory, and then finally committing the results or writing back the results back to some register storage. That is true for all processors. So we talk about it in terms of MIPS, and the MIPS developers and the authors of the original MIPS papers in the textbook are pretty good at breaking it down. But that's true for all processors, that they would have generally those 5 stages, and the design decision we get to make then is, you know, how many clock cycles it's going to take for that implementation, what kind of trade-offs we may have between the latency and the throughput of a given implementation. But for our starter implementation, we can start to call it our project part B implementation. It's also our lab 4 implementation. Our starter implementation is absolutely making that assumption that in terms of our critical path analysis of read register, big old cloud of combinational logic, and then write register, that's absolutely how we're implementing our processor. That's why this is referred to as, the so-called single cycle processor. So we in fact would have a critical path in our implementation of this single cycle processor. We wouldn't at all have the ability to know exactly what that path is, right? That's going to require the synthesis tools to analyze our VHDL code, target a given underlying hardware fabric, whether it be an FPGA or a custom circuit we're designing for an ASIC, and give us an actual precise result back. That's what will tell us if it's 1 nanoseconds or 20 nanoseconds or anything in between. But in the context of these major function blocks, um, we can actually analyze what our critical path is going to be. And we can use that information to help us further optimize this implementation. All instructions read from the program counter. All instructions have to actually, that was weird. All instructions have to actually fetch something. Okay. All instructions have to then decode that fetched instruction, and most instructions have to read from the register file. Not all instructions require this execute stage, so certain instructions are done right here, right? Jump instructions don't have to do anything, right? Jump instruction just says, "Oh, I've decoded. I've determined that I am a jump. Let's just update the program counter. Done." Most other instructions, though, after they've read, they've decoded, they read from the register file. They also then have to do an execution. For other instructions at that point, they're done. Your R-type instructions: fetch, decode, do the math that's required. That's our execution stage. And then finally write the result back into the register file. We know, and the mem stage, again, another word for that would be like data memory stage for that 4th block that we have here. For that mem stage or that data memory stage, there's only a couple instructions that actually need that stage at all. Those are our lab 4 instructions: store words, load words, and all of the store and load variants. The rest of the instructions, in terms of the path they take through this single cycle, don't have to use that block at all, right? Your ALU instructions, your add immediates, those things of that nature, they go through all of these stages, but they can entirely skip that stage entirely and physically skip it as well, right? The wires that are the output from your ALU, we connect them to the address port of our memory module for that mem stage. But if it's not needing it, in terms of the critical path for that instruction, we don't have to measure that time. But for our loads and stores we're required to, stores are done when they get to this point because we're actually writing a result back to the data memory and then we're done. But it's our load instruction that actually has to go the rest of the way through. And finally, load the result from memory and write the result back into our register file at the end. So if we have these and I would call it 5 stages, 1, 2, 3, 4, 5 stages of any instruction's execution, some of them just use 2, right? The best example would be a jump instruction. I've fetched the jump instruction, I've decoded the jump instruction, I'm done. Oh, it's a jump. Don't have to do anything else. Some other ones use roughly 4, right? Store word instruction. I've fetched. I've determined it's a store. I use my ALU to do the address math for me. and then I write the result into the memory. That's 4 stages. Only one instruction of these actually uses, of all the ones we've learned so far, actually uses all 5 of these steps, and that would be the load word. Load word is the only one that we fetch, we determine it's a load, we do our address math using the ALU, like your Lab 4 design. We use the memory module, our data memory module, to read from the data memory. And then we still have that final step. We're not done yet. We then still have to finally write back, that's what WD stands for, write back that result back into the register file. So while we would need synthesis and other tools to tell us precisely what the critical path is in our processor, like literally how many nanoseconds it is and how far it has to travel through the processor, we actually know enough about MIPS at least and the design of our MIPS ISA and the resulting architecture that for our processor, we actually know not the specific precise path, but we actually know that load word is our critical path. Or a path that only exists to support the load word instruction, it would be another way to phrase that, is the critical path of our processor. Because it's the only instruction that has to, of all the various paths through this logic, and that was my attempt to illustrate here that there's many, many such paths. But in our case, of all the very big picture paths through our processor, only one instruction has to actually go through all of those major steps. And in terms of our implementation, again, the critical path of our processor is a physical thing. It dictates for our logic not to be totally glitchy what we can set our clock frequency to be. Basically, it's the inverse of our critical path is what we can set our clock frequency maximum to be. And for our MIPS implementation, for a single cycle implementation of our MIPS, in which our goal is to get the entire instructions done in one single cycle, it's the load word instruction. And the logic to support the load word instruction would be another way to phrase it, I guess. It's the load word instruction that is the critical path of our MIPS processor. And a common approach, if we want to improve our critical path, in this case, we see there's this sea of logic, and it's too long for our purposes. We want to get it down to 1 nanosecond, and we can't. There's other optimizations that can be applied, but a very common approach that would be applied would be to say, okay, our combinational logic has some paths in there, or at least one path in there that's too long. Let's split up that path. Let us add additional registers in our design such that there's now maybe twice as many paths, because there's paths to the left of the register and now paths to the right of that register. But those paths are presumably, this is all very hand-wavy now, roughly half the length, very, very roughly half the length, right? We kind of split the circuit directly in half and said, well, the paths are too long, let's add a flip-flop or add a register in the middle of all those paths. And now the path will be very roughly, half the length they were before. And maybe we can get very roughly twice the clock frequency we could have before. We'll talk about that in a second here, but in terms of what that means for our single cycle implementation, we can also do something very similar here. And there's a reason we break it down into these logical blocks is that this is the most obvious place to do that subdivision of our 5 stages of execution of a given load word or other instruction here. That in the single cycle implementation, and again, you're almost done with that in terms of implementing it, all of this is happening, it's all combinational logic, right? We think of that mem component, your data memory, as having a clock on it, and it does, but that's only for writing to it. So the instruction ends when that write happens for a store word. So it's still combinational read. So we read and we get everything read and we only write at the very end of the instruction. That works. That leads to a single cycle implementation with potentially a long critical path. So the next step would be breaking up that critical path. Maybe potentially let's break it up in half. But the common approach that's taken is to take these logical steps and break them all up individually. So they all each have their own clock cycle associated with them. And if the previous diagram without those blue registers added was um, the single cycle processor, what we'll then next be learning about is the sort of pipeline processor. But when I talk about and let's get back to performance here. When I talk about the metrics we use to measure computing performance, even at this architectural level, even comparing those two design decisions is actually quite tricky, or it can become quite tricky. Just like with the two airplanes, the different examples of the airplanes, we can't clearly say, this airplane is a better design than this other airplane. For this example, where we go from a single cycle processor where everything gets done in one relatively slow cycle to a quote unquote pipeline processor where instruction gets executed over now what would be five clock cycles, we can't immediately say with any certainty that one implementation is better than the other in terms of performance because there's a trade-off involved. And the trade-off involved is the clock frequency that the blue processor would be able to execute at versus the latency associated with that blue processor's execution. Now it's going to be, instead of one relatively slow cycle, it's going to be five relatively fast cycles for the execution of that instruction. And for the latency of that individual instruction, we have to do a little bit more analysis to say for certain one way is quote unquote better than the other. But I went a little bit into outer space here. Let's get back to this concept of our measuring and our metrics for computing performance relative to the physics one kind of way of looking at it. Let's get back to the units here. So when we talk about our clock ticks for our execution, the main thing to remember is that for all of our digital hardware in general, our operation of that hardware is governed by a constant rate clock. So we have this characteristic of our implementation, which is alternately either the cycle time, that's in nanoseconds, or it could be in picoseconds, or our clock rate. They're the same metric. It's how many cycles per second can this digital hardware be operated at. So instead of worrying about the execution time for something in just seconds, we can break it down into clock cycles and convert from clock cycles down to seconds. So in the same way we went from meters per second to total meters at the end of the day for calculating my running distance, we can do the same exact thing when measuring our computing performance. And just as long as we keep track of our units, that for a given program, we will require a certain number of clock cycles to execute it. And consequently, for our program as executed on a given implementation, there'll be a certain cycle time associated with it. And we can relate the two things together to measure out performance, at least in this case, the latency of how many seconds does it take to execute that entire program. And so we have that vocabulary that we can use to relate things together. A given program will require a certain number of instructions, and that's our MIPS assembly instructions, a certain number of clock cycles, and then consequently a certain amount of time associated with that. And so this vocabulary allows us to do that direct relation. We have a cycle time, which is how many seconds per cycle for execution. That's the inverse of our clock rate. And so you can think of those as two different things, but they're the same exact thing. Our 1 gigahertz is our 1 nanosecond clock. It's the same thing. You can use the terms interchangeably. And it's good to keep track of some of those. We've been using a 100 nanosecond clock in lab. It doesn't matter for model simulation purposes, right? We could have done whatever we want. That would correspond to a 10 megahertz implementation. It's good to keep track of those powers of 10 when they get to around 10 to the ninth for computer architecture purposes, keeping track of our performance. But 1 gigahertz, that's 10 to the ninth. 1 nanosecond, that's 10 to the negative ninth. That's good enough, and you can work from there. And then the vocabulary we can then use to keep track of how many instructions and how many seconds our program requires would allow us, we could do that via determining how many instructions are needed by the program as whole and how many cycles on average we need to execute a given instruction. We think about our implementation that is either a single cycle implementation, or in this case, a pipeline implementation, an implementation in which it takes one cycle per instruction, which we're very close to already having built, or an implementation that takes, in this case, 5 cycles for a single instruction in isolation. But the truth is, and as we learn more about this pipeline design, we'll explore this quite a bit more. The truth is, in our actual implementation, once you add these registers, life gets a lot messier. And the last 5 weeks of lab will be spent cleaning up that mess once you add those pipeline registers there. And the actual cycles per instruction now will vary depending on what the instructions are. Another way to think about this, although it's not strictly correct, it's a good way to visualize what could be happening here, is we have these 4 blue registers now, and I mentioned it takes 5 cycles to execute. But for our jump instructions, in theory, we don't have to take 5 whole cycles to execute, right? Because as we mentioned, we fetched the jump instruction, we've decoded the jump instruction, we're actually done. Hey, it's a jump. Don't do anything else. Just change the program counter and move on with life, right? In theory, at least, our jump instructions could be executed in just 2 cycles in that blue processor we have here. And our ALU instructions, our adds and subtracts and shifts and whatnot, in theory could be executed in fetch, decode, execute, skip the memory, write back stage. In theory, those could be executed in 4 cycles. And I'll keep saying in theory, I guess. It'd only be the load word instructions in theory that could execute, that require all 5 of those cycles. So in practice, the amount of cycles, the amount of clock cycles, the number of clock cycles it takes to execute an instruction varies depending on which instruction it is. In practice, in reality, I mean, in terms of real implementations of real pipeline processors, including the ones we're building this semester. For the single cycle processor, it's a tautological thing where everything executes in 1 cycle. So we have a cycle per instruction of 1. And that's thought of as some sort of ideal. That's as good as you can do. You have to take another course to learn about how we can do better than that. But in terms of our pipeline processor, though, we now potentially have a varying number of cycles it takes to execute our instruction, depending on what the instruction is. And so consequently, we have this metric that becomes pretty important for us in terms of understanding our computing performance based on our underlying implementation. And long story short here, and I know we have to end class at some time. I could go forever at this rate. The textbook introduces these performance considerations so early on, but this concept like CPI doesn't really make much sense outside of our understanding of what's happening inside the processor. And what's happening inside the processor is a varying number of cycles per instruction, depending on what the instruction is. And so consequently, and we'll tie things together here, we can only measure the performance of our application on our underlying processor by knowing not just the implementation aspect of our processor, but by also knowing the aspects of our application as well. If our jump instructions only take 2 cycles, but our load words take 5, and the reality isn't quite so clean even for our MIPS, but it's a close enough starting point for us, the CPI, the cycles per instruction, which directly relate to our performance, is going to be a function of what our relative instruction mix is of how many jumps versus how many loads versus how many other types of instructions that maybe take a varying number of clock cycles. So it's analogous to what we're doing with our physics of our measuring speed, and we have that clock rate, which is very close to like a speed metric of how many times your foot is hitting the ground when you're running. It's a cadence for our processor. But the actual performance of our processor has these other considerations that's going to make us take a little bit more time to measure that and explore that on Wednesday. What would be nice is if everyone, and it's pretty easy reading, look at that section 1.4 to 1.6 in the textbook between now and Wednesday. And I think you'll have a pretty good feel for this, and then Wednesday can be a little bit more review for us. You'll get some experience with doing physics type problems for these type of questions, where the trick is just to keep track of the units that you're using so you don't wind up with a result that seems nonsensical. But the concept itself is something we should be able to get through, by the end of Wednesday if you've done a little bit of reading in the meantime. Otherwise, good luck as you complete your Lab 4s and start working on your project work this week. And look forward to seeing everyone on Wednesday. Thanks.